Hello my dear student. Today let us talk about limit of a sequence of measurable functions. We want to know whether the limit function of a sequence of measurable function is measurable or not. We want to know that one. Last time we have discussed how to construct measurable function from two measurable function. So sum of two measurable function is measurable, difference of two measurable function is measurable, and then product of two measurable function is measurable. Okay, and then multiplication of a measurable function by a constant is measurable. So those things we have discussed. Those are the method of constructing a new measurable function from the existing measurable functions. And this one is also one of the method of finding new measurable function. You have a sequence of measurable function, the limit of the sequence, okay, is also measurable. So this is the theorem. Let Fn be a sequence of measurable function defined on the same measurable set. Okay, the domain of definition of each member of this sequence is same, and the domain is a measurable set also. Then supremum or maximum function. Okay, if n is finite, 1 to n, this supremum is also another name is called maximum function, is measurable for its n. Infimum, if n is infinite, if n is finite, this infimum, it has another name, that is minimum. Okay, minimum function is measurable for its n. Okay, if n is 100, you find out the minimum of these 100 functions. Okay, that is also measurable. Supremum, so just supremum means the supremum of this n is going to up to infinity. You have a sequence of function. Okay, for that you take supremum. Okay, so for in this step, in this step, what you have in this step, it is finite. For finite case, it is called maximum, or for notational convenient, it is denoted by supremum also. So but when n tends to infinity, we just write, when n tends to infinity, we just write supremum. Okay, then when n tends to infinity, this infimum function we just call infimum Fn. So then limit supremum, we can talk about limit supremum is also a measurable function. Then limit infimum is also a measurable function. So let us briefly recall how we define this supremum. Okay, how we define this supremum. Let us, and this infimum, and then this supremum, then this infimum. Okay, and limit supremum Fn and limit infimum Fn. Let us briefly recall it. Okay, so let me open this window here. Okay, so suppose if you have two functions, let us consider the case when you have n is equal to 2. Suppose you have two functions, f1 and f2. Okay, suppose f1 of f1 of say 1, you evaluate this is equal to say 4, and then you evaluate f1 of f2 of the same point 1 at 1, this is equal to say suppose 5. Okay, then what is the maximum of this? What is the maximum of this one? Maximum is 5. No? Then we say that supremum of say I, which is going from 1 to 2 fi at the point 1 is equal to what? 5. Okay, all right, so f1 and f2 are two functions. Okay, then we define a new function like this, okay, the name of the function is supremum I running from 1 to 2 fi. Here I sorry, this is fi at the point 1 is equal to 5. Okay, so how about the minimum? What about the minimum? You find out the minimum here. Infimum of, say, I is running from 1 to 2, or f of I at the point 1 is equal to, what is the minimum? Minimum is 4. Alright, so given two functions f1 and f2, you now construct two functions. One is maximum or supremum I running from 1 to 2 fi. Another one is infimum or minimum infimum I is running from 1 to 2 fi. So you can construct two functions. Okay, right. So suppose this can continue, I is equal to, if n is equal to 3, you will get 3 function. If n is equal to 4, you will get 4 function. Okay, so like that you will define, for each n you can define supremum. I is running from 1 to 2, you will define infimum also. I is running from 1 to 2. So if n, for any n 100 also, you can define like this, minimum or maximum like this, or supremum or infimum like this, you can define. So this is the way of defining supremum for finite cases. Okay, and then let us see what is discuss about f1 minus f1 minus f2. You think about minus f1 and a minus f2. So then what is minus f1 of 1? So f1 of 1 is equal to 4, no? So if you multiply by minus, it will be what? Minus 4. Then you think about minus f2 of 1. f2 of 1 is what? f2 of 1 is 5, no? So multiply by minus, then you get minus 5. Then what is the supremum? So these two, which one is greater? Minus 4 is greater than minus 5, right? Then supremum of minus fi at the point 1. So here I is running from what to what? 1 to 2 is equal to how much? It is equal to minus 4, right? So then you think about the infimum again. Infimum of minus fi at the point 1. So here I is running from 1 to 2. Okay, so what is the minimum? Minus 5 is minimum. Okay, right, smallest one, smaller than minus 4. So this will be minus 5. So you see from here, you see what happened. Let us see from here. Okay, so supremum, this supremum at the point 1 is 5, is equal to minus of this infimum. When you take minus fi, if you take infimum, so what is that? That is equal to minus of supremum. So generally what? Generally you can write this one. Generally what you can write is infimum of minus fi. Okay, let us talk about n. N for any n is equal to what? Is equal to minus of supremum of I running from 1 to n minus, no, so fi. So minus here, let us put positive here. Okay, infimum of sequence of function is equal to minus of supremum of minus fi. This equality you get. Okay, so from this example clearly you see this equality. Infimum of any finite sequence of function is equal to minus supremum of negative of that finite sequence. Okay, so this equality is there. Okay, so this is very important. We will be using this equality, and will be it will be used in the proof of the theorem. Okay, so that one is there. And then let us talk about limit supremum and limit infimum. Let us talk about limit supremum and limit infimum. Okay, what is limit infimum and limit supremum? Limit infimum fn, there are two concepts. Limit supremum, limit supremum fn. So this means you take n from 1 to infinity. Okay, this means you take limit n is going from 1 to infinity. Here it means you are not considering finite sequence of function, you are considering infinite sequence of function. Okay, limit supremum fn, limit infimum fn. Okay, so what is, there are two definitions. One is for this sequence of function. For this sequence of function, what do you do? At each point evaluate the sequence of function. Suppose f1 of 1, f1, f2 of 1, like this. You evaluate at a point. So then at that point you have sequence of real number. Okay, the sequence of real number. Then that sequence of real number will have lots of subsequences. Okay, the subsequences converges to a limit. All right, so lots of subsequences are there. So you just think about the limit point of each subsequences. So the greatest one is called limit supremum. Okay, so what you have to do, at a given point you evaluate the value of the function f1, f2 also, f3 also, like this. Then the evaluated points are real number. So you have a sequence of what? Real number. For this sequence of real number there are lots of converging subsequences. Okay, there are lots of converging subsequences. So converging subsequence, for those converging subsequence you think about the limit points. Okay, the limit of conversion. Okay, the converging points you think about. So from this you find out the greatest limit, that is called limit supremum. Okay, the greatest limit is called limit supremum, and the smallest limit is called limit infimum. Okay, at this point you find out that you will give a new function. That function is called limit infimum fn, and another function that is called limit supremum fn. So this is one way of defining, one way of defining limit supremum and limit infimum. And next is, you just think about here, just think about f1 is here, sequence f2 is here, f3 is here, f4 is here, and goes on up to infinity. All right, then you evaluate value of this function f1 at the point 1, this one also, f2 at the point 1, f3 at the point 1, f4 at the point 1. Okay, then what do? You find out the greatest one. So here one value will be here, another value will be here, another value here. So out of these values you find out the greatest one, or supremum one. Okay, let it be here somewhere. Okay, the greatest will be here. And then in the next step, what do? You take it out this one, you take it out this one, and start from here, f2 at 1, f3 at 1, f4 at 1, like this. You keep on going evaluation. Then from here again you find out the greatest one, maximum one. So you have two supremum now, one including f1, another one excluding f1. So which one will be greater? So the earlier one will be greater, right? The earlier one. So supremum including f1 will be greater, no? So the new supremum will be less. Okay, like this. It will be less or equal. So you keep on doing like this. At the third step, you take out f2 also. Then from f3, you find out f3 of 1, f4 of 1, like this. Okay, you find out the greatest one from starting from here, the greatest one or the supremum one. So that will be still smaller than the earlier two supremum, no? So you keep on doing like this. Then ultimately it will stop somewhere here. Okay, as n tends to infinity, it will stop somewhere here. All right, so that is the smallest, that is the smallest what, that is the smallest, you know, supremum, no? That smallest supremum, we call it what? Limit supremum. All right, limit supremum. So next, from here again, you evaluate f1 at 1, f2 at 1, f3 at 1, f4 at 1. Then you find the smallest one, infimum, the smallest one. So smallest one will be somewhere here. Okay, smallest one will be somewhere here. And the next step, you take out f1 of 1, then start from here, f2 of 1, f3 of 1, f4 of 1, like this. Okay, so after deleting this one, you have another sequence of real number. Now you find out the infimum one, the smallest one. So the first infimum and the second infimum, which one will be greater? Okay, the second one will be greater, no? So it is easy to understand that one. The second one will be greater. So second one will be here. The third one will be, you know, again you take out this f2 of f1 and f1 of f1. No? Then you start from here, you find out the infimum or the smallest one. The new infimum will be greater than the earlier one. So it keeps on going like this. Okay, so lots of infimum are there. The greatest one will be somewhere here. Okay, the greatest one will be somewhere here. This is called limit infimum. Okay, so limit infimum, this is called a limit infimum, and this one is called limit supremum. So from this explanation, it is very obvious that limit supremum will be always greater than or equal to limit infimum. So here, in this way, how we define limit infimum, limit supremum. Let us see. Limit supremum of fn is equal to infimum of supremum fn. Okay, so fi, I is greater than or equal to n. So this way you keep on for every n is equal to 1, you find one supremum. N is equal to 2, you find one supremum. N is equal to 3 also, you find one supremum. So many supremum are there. The infimum, the smallest one, so supremum is there. So it keeps on decreasing. No? You find out. So the smallest one will be here, that is called infimum. Okay, the smallest one, this is called limit supremum. So this one, how we define this one? Limit infimum fn, this we define like this. This is equal to supremum of infimum fi, where I is greater than or equal to n. Okay, so when I is equal to 1, you find out the infimum here, the smallest one. When I is equal to 2, n is equal to 2, you get infimum. It keeps on increasing, you know. I explained it is increasing. Okay, it keeps on increasing. So the greatest one, supremum one, will be somewhere here. Okay, so this we call it limit infimum. Okay, so from this explanation, it is very obvious that limit supremum is always greater than or equal to limit infimum. Okay, so in some sequences, these two are equal. Okay, these two are equal. Limit infimum is equal to limit supremum. In some sequences, converging sequence of function, you know, if the sequence of function converges to a function, then limit infimum is equal to limit supremum. Okay, and that equal value, just we call it limit of the function, limit fn. So we'll drop here limit infimum supremum. The equal value, we call it just limit of the sequence of function. Okay, so this is the idea. This is the idea of limit supremum, limit infimum, and for finite cases, for infinite cases also. Okay, so after understanding this idea, now let us go back to our theorem directly. Okay, so let us first prove that this limit, this limit supremum is finite case, is measurable when each member of the sequence, finite sequence, the supremum is also measurable, the infimum is also measurable, like this. And this is for infinite cases. Okay, for infinite cases we drop this. For infinite cases, I is running from 1 to infinity, then we drop this one and it is denoted by this one. For infinite cases, here also we drop this one here and just fn is written. Okay, limit supremum, and then limit supremum fn and limit infimum fn that we just talk about. Okay, first let us prove number one. Let us first prove. Okay, so for a given alpha, for a given real number alpha, okay, for a given real number alpha, let us first prove that equalities of these two set. Okay, this is a set x. What is this set? X such that supremum fi x, I is running from 1 to n, is strictly greater than alpha. This set is equal to union of this set. What is this set? X such that fi x is greater than alpha. So now let us establish equality of these two sets. Okay, let us now establish equality of these two sets. So what is the normal method? You take 1 point from here and prove that that is a member of this one, and conversely you take 1 point from here and that point is also member here, then equality established. Okay, that is the method. So first let us take one arbitrary point from the first set. Okay, so see, x be an arbitrary point, so don't get confused this x and this x. So x is an arbitrary point here. Okay, if that point, if the element x is a member of this set, then the supremum I running from 1 to n fi x should be strictly greater than alpha. Okay, that is from the definition of the set. Okay, so then there will be one function which will give you the maximum value. You are evaluating maximum value of the function f1, f2 up to fn. So one function will give you the maximum one. So suppose the index j gives you the maximum value. Okay, the maximum value is given by the j, where j is less than or equal to n, such that this one. Okay, so this is supremum occurs. Okay, at this j. All right, so that means what? That means what? X belongs to x such that, so this should be j. Okay, this should be j. So x such that f of j x is greater than alpha. Okay, so that means what? X is a member of this union, because at some point of I, and when I is equal to j, the point x is a member, right? Therefore in their union is the point x is also a member. Okay, so x is a member of this union. All right, so whenever you take one point from this set, that point is also a member of this union. Okay, so therefore you establish the inclusion. This is a subset of this one. Okay, this is a subset of this one. So this is very obvious. And conversely, let us take 1 point from here. Okay, conversely, let us take 1 point from here. So x is a point from here. All right, so then x is a member of this one, union I running from 1 to n. So x should be at least member of one member of this union. So then x is member of this one for some j. Okay, for some j. Okay, so since supremum or the maximum one will be greater than each member, you are finding out the maximum or supremum of n function. So that will be greater than each individual function. So it will be greater than also this one also. Or okay, but this one is greater than alpha, therefore this function is greater than alpha. Okay, So since this function is greater than alpha, this x, okay, this x is a member of this set. All right, what is the set x? Such that supremum fi x, I is running from 1 to n, is greater than alpha. I am missing here the here, it is greater than alpha. Okay, this is greater than alpha. Okay, and curly bracket finish here. Okay, x such that supremum of fi x is greater than alpha. So x is a member of this one. Okay, so you take one arbitrary point from here, that point is also member of this one. All right, so what does it say? It says that what? It says that this set is a subset of this set. So therefore the equality is established, you know. So ultimately what you have, this set is exactly equal to this set. All right, so what we want to prove that supremum fi I is running from 1 to n is a measurable function. So therefore for every alpha real number, we want to show that this set is measurable. If that case happens, then the supremum function is measurable. Okay, but this set is equal to this one. Let us see what is this set. So is fi is measurable, so for every real number alpha, this one x such that fi x is greater than alpha is a measurable set. Okay, so therefore this is a union of measurable set, therefore the whole thing is measurable, means this set is measurable for its alpha. So therefore this function is a measurable function, hence supremum I running from 1 to n fi is a measurable function. Okay, it is a measurable function. So the first case is over now. If you understand the first case very clearly, the second case is just, you know, follows from my explanation just before proving this theorem. Okay, so now number 2, we know that I have already explained that one. We know that, you know, infimum of a function is equal to minus of supremum of negative of the functions. All right, this one. So since fi is measurable, minus of fi is measurable, that one we have done it. Okay, and it's, and then just now in case 1 we have proved that supremum of a sequence, finite sequence of function is measurable. So this minus f1 minus f2 up to minus fn is also finite sequence of measurable function. Its supremum is also measurable. Okay, all right. So this supremum function is now measurable. It is multiplied by a constant minus 1. So the result is also a measurable function. So ultimately this one is measurable. Okay, so it is very straightforward. Okay, so therefore infimum fi is also measurable. All right, so next, you know, number 3 is the case when n tends to infinity. When n tends to infinity, we just simply write supremum. Okay, we simply write supremum. All right, so when n is equal to finite, it was the union was from n I running from 1 to n, no? Or n running from 1 to n, some m. Okay, but when n tends to infinity, from case 1, this set is exactly equal to union, countable union, n going from 1 to infinity, like this. Okay, it is very straightforward. When n tends to infinity, this set is exactly equal to this set. This is coming from case 1. We just extend n up to infinity. Okay, this equality is established. Okay, so each function fn is measurable, therefore this set is measurable. For each alpha, this set is measurable. So this is a countable union of measurable set. It is measurable, therefore this set is measurable for each alpha, therefore the supremum function fn is also measurable. All right, so fn is measurable. Okay, so this is measurable. Next, again same, number 4, infimum of fn is equal to what? Infimum fn is equal to minus of supremum of minus fn. Okay, just in case 2, you have a sequence of function f1 f2 f3, you multiply that one minus 1, no? Then you have another sequence of measurable function. Okay, so by case 3, supremum of a sequence of function is measurable. So this function is a measurable function. So if you multiply that measurable function by a constant minus 1, that is also a measurable function. Therefore infimum fn is measurable. Okay, and infimum fn is measurable. All right. So next, number 5. Let us see number 5. Yeah, from that second definition, limit supremum fn is equal to what? Infimum of supremum I running from 1 to I is greater than or equal to n. Okay, fi, this one. Okay, so for each n, this is a measurable function that we have done it. Then you have a sequence of measurable function. All right, then you take infimum, that also we have done it, that is also measurable. Okay, so that therefore by case 4, limit supremum fn is measurable. Okay, so this is for each n you get a function here. If n is equal to 1, you get a function here. If n is equal to, you have a function here. So how many such function? You have sequence of function up to infinity. For that you take infimum. No, for that you take infimum. The infimum is measurable. It was discussed in what? Case number 4. Therefore this is measurable. That means what? Limit supremum is measurable. Okay, it is very straightforward. So similarly, limit infimum fn, by the same thing. Okay, limit infimum fn is also measurable. Okay, it is very straightforward. So it is measurable. Note, if the sequence has a limit, then in that situation limit supremum fn is equal to limit infimum fn. The same value, the equal value, okay, the common value, we call it limit fn, and this function is also measurable. Okay, so here I want to give some emphasis to you. You have to be very clear in defining what is supremum and infimum for finite case, for infinite case. Okay, if your concept is very clear, I just explained just in the beginning of the theorem, in the pant window, I just explained how we define supremum in finite cases, infimum in finite cases, supremum in infinite cases, infimum in infinite cases. I have explained you briefly. So if those concepts are very clear to you, and this theorem is very easy. Okay, if those concepts are very clear to you, so try to clear those concepts. If you have some doubt, you can talk to me through telephone, or you can discuss with me in a WhatsApp group, in our WhatsApp group. Okay, so I give this one, I give emphasis. Again and again I am telling you, try to clarify the concept of definition of supremum for finite cases, infinite cases, like that. And similarly for limit supremum fn, limit infimum fn. Yeah, this is very confusing, so you have to read again and again what I have explained to you. You watch it again and again, then digest it, then you take pen and a paper, you write down in your own language. Okay, then you will understand. That is the only thing. To understand mathematics, you have to use pen and a paper. Just read it, then write it down without looking at the note. Okay, so that much I want to give today, although it may be very small, but the concept is very, very intense. So you have to understand those concepts very clearly, then you will understand this one. Okay, so thank you very much. All the best.